In June 2017, geologist Marie Jackson and her collaborators at UC Berkeley and the University of Utah published a paper in American Mineralogist that quietly broke a 2,000-year-old riddle. Her team drilled concrete cores out of the submerged Roman harbor structures at Portus Cosanus on the Tuscan coast, piers continuously soaked in the Mediterranean since the reign of Augustus. They ran those cores through electron microscopes and synchrotron X-ray beams at Lawrence Berkeley National Laboratory. What they found should not have been possible. Inside the matrix, an unusual mineral called Aluminous Tobermorite was still forming, still growing, still interlocking, plate by microscopic plate, after 20 centuries underwater. Modern marine concrete is engineered for a service life of 50 to 100 years. After that, the steel rebar corrodes, the matrix decays, and the structure must be torn out and rebuilt. The Roman piers do the opposite. The longer they sit in saltwater, the stronger they become. The sea, instead of destroying them, becomes the ingredient that builds them. This is Oracle Prime. What you are about to hear is not romanticized lost wisdom. It is peer-reviewed laboratory results, a documented record of medieval cannon fire that bent against dirt and ash, and a building method so structurally simple it has been re-derived independently on every inhabited continent. The active ingredients are within walking distance of where you are standing right now. Part 1. The Pantheon is not the exception. To understand what Marie Jackson found, step back to a single building that has been quietly humiliating modern construction for 19 centuries. In Rome sits a circular temple completed around AD 126 under the Emperor Hadrian, converted to a Christian church in 609. Which is the main reason it survived when most other ancient temples did not. It is called the Pantheon. Its dome spans 43.3 meters, about 142 feet, and it has stood for almost 1,900 years without a single steel reinforcement bar, retrofit anchor, or tensioning cable. It is still, today, the largest unreinforced concrete dome on Earth. Larger than St. Peter's, larger than Florence Cathedral, larger than anything we have managed to pour without metal since. The Romans had two ingredients we no longer commonly use. The first was Pozzolan, fine volcanic ash mined near Pozzuoli, just outside Naples. The second was hot quicklime, used in a way modern textbooks dismissed as sloppy and unscientific for nearly 2 centuries. As of January 2023, that judgment has been completely overturned by MIT, and we will get to exactly how shortly. The Roman architect Vitruvius, writing around 25 BC in De Architectura, recorded the working ratio: 1 part lime to 3 parts pozzolana for above-ground work, 1 to 2 for anything submerged in seawater. He did not understand the chemistry. He documented the practice that worked. The piers at Portus Cosanus and the breakwaters around the Bay of Naples are the same structures Marie Jackson has been drilling cores out of for the last decade. None require maintenance. None have been repaired. The concrete is still chemically active. It is, in the most precise sense of the word, alive. Part 2. When a 27-foot cannon broke against dirt. Travel about 1,300 kilometers east across the Mediterranean to the city the Roman engineering tradition followed when the western capital fell, Constantinople. Founded by Constantine on the European edge of the Bosphorus in 324 CE. Expanded under Theodosius II in the early 5th century. By the time the Visigoths sacked Rome in 410, The imperial government in Constantinople was watching the Western Roman world collapse in real time. So they built walls. Not just walls, the Theodosian Walls, a 4-line defensive system stretching 5.7 kilometers from the Sea of Marmara to the Golden Horn, a flooded moat 15 to 20 meters wide, a breastwork, an outer wall 8.5 meters tall and 2 meters thick, and then the inner wall, 12 meters tall, 4.5 to 6 meters thick, reinforced with 96 polygonal towers rising up to 20 meters above the parapet. But the Theodosian engineers had no Vesuvius, no natural volcanic ash. So they invented an artificial Pozzolan. They took fired clay bricks, ground them to coarse powder, and mixed that brick dust with slaked lime, river sand, and rubble aggregate to form the mortar core. The chemistry was identical in principle to Vitruvius. The reactive silica and alumina in the fired clay locked onto the calcium hydroxide in the lime, growing crystalline calcium silicate hydrate gel through the rubble. The horizontal red bands you can still see across surviving sections of wall in modern Istanbul are not decoration. They are structural seams designed to dissipate seismic shock and bond the limestone facing onto the mortar core. For more than 1,000 years, that wall did its job. The Avars failed against it in 626. The Arab Umayyads failed in 674 to 678, and again in 717 to 718. The Bulgarians, the Rus, the Crusaders of the Fourth Crusade, every army that approached Constantinople by land broke against the Theodosian system. Earthquakes in 437, 447, and 740 cracked sections. The city repaired the damage in weeks, and the walls held. Then in 1453, Sultan Mehmed II arrived with 60 to 80,000 troops, more than 300 ships, and a piece of artillery without precedent in the medieval world. The Hungarian engineer Orban had cast for the Sultan a bronze bombard nicknamed the Basilica, 27 feet long, 8 inches of solid bronze barrel walls, a bore 30 inches across. It fired stone balls weighing roughly 1,200 pounds, and when it discharged, the report could be heard 10 miles away. Mehmed positioned it directly opposite the Mesotichion section near the gate of St. Romanos. From the 11th of April through the 28th of May, 48 days of relentless bombardment, Orban's gun and dozens of supporting cannons hammered the wall. The wall did not behave like stone. When 540 kilograms of granite slammed into the dense earthen and ash matrix at terminal velocity, the projectile did not split the wall the way it would have shattered a granite block. The matrix deformed locally. Compacted particles slid against each other. The kinetic energy was absorbed into sheer mass and redistributed through the rubble core. Each shot eroded the cannonball nearly as much as it eroded the wall. Reload time was 2 to 3 hours. Overnight, defenders patched breaches with timber, earth-filled barrels, and wool bales, and by morning, the patched section behaved exactly like the original mortar. The Theodosian walls were never breached by force in 1453. The city fell on May 29th because, late in the final assault, a small postern gate called the Kirkoporta was found unlocked, and a unit of janissaries poured through. The defenders, outnumbered roughly 10 to 1, were overwhelmed in close combat. The city was lost. The walls were not. The basilica cannon itself had cracked apart from its own discharge and sat silent on the morning of the assault. Brick dust, slaked lime, river sand, rubble. That is the 4-ingredient recipe that defeated the most powerful artillery piece in 15th century Eurasia. Part 3. Why we stopped building this way. If this material is so good, If it absorbs cannon fire, ignores earthquakes, and grows stronger across 2,000 years of saltwater, why did the world abandon it? Most channels get this wrong. There is no conspiracy, no buried memo. There is, instead, a perfectly clean story of industrial economics that explains every step of how lime pozzolan construction was displaced. In 1824, an English bricklayer named Joseph Aspdin patented a process for grinding limestone and clay together, firing the mixture, and grinding the resulting clinker into a fine powder. He called it Portland cement. 20 years later, Isaac Johnson refined the kiln temperature to produce true modern Portland clinker. By 1900, it was being manufactured at industrial scale across Europe and North America. By 1930, it had become the default global binder. The lime pozzolan tradition Vitruvius and the Theodosian engineers had used was, within a single human lifetime, almost entirely displaced. What Portland cement offered was not better engineering. It offered a better business model. Lime pozzolan rammed earth cures slowly, over months and years, and gains strength continuously across decades. Portland cement reaches roughly 70% of design strength in 28 days. For a developer building a 30-story tower on a financing schedule, that difference is the difference between a profitable project and a bankrupt one. Lime pozzolan ingredients are scattered across local geology and local waste streams. Portland cement is manufactured in centralized factories, bagged for shipping, and trucked anywhere with predictable performance. For a global construction industry that needs uniform standards across thousands of job sites, centralization is a feature, not a bug. Lime pozzolan formulas vary with the local soil. Portland cement formulas can be patented, branded, certified, and standardized. ASTM, EN, Bureau of Indian Standards. Every concrete sold today is graded against a Portland baseline. None of that exists for the older method. Not because anyone forbade it, because nobody had a financial reason to build it. None of this is conspiracy. It is market selection. Portland cement won because it fit the economic shape of 20th century construction. But economic optimization comes with costs the original engineers never had to count. Modern Portland cement production accounts for roughly 7 to 8% of global carbon dioxide emissions, about 1.6 billion metric tons of CO2 in 2022, with a trajectory toward 3.8 billion tons per year by mid-century. Roughly half of those emissions come from chemistry. When limestone is calcined at over 1,400 degrees Celsius, it releases CO2 as a stoichiometric byproduct, regardless of how clean the energy source is. The other half comes from the heat itself. A lime-stabilized rammed earth wall has roughly 1/10 to 1/5 the embodied carbon of an equivalent reinforced concrete wall. The earth requires no firing. The pozzolan, when it is wood ash or rice husk ash or crushed brick, is already a waste product. The lime requires firing, but at lower temperatures, in much smaller quantities, and absorbs CO2 back out of the atmosphere over its lifetime through carbonation. This is not a moral argument. It is an engineering argument with implications for anyone planning to build, retrofit, or maintain a structure they want to outlast their grandchildren. Part 4. What might found in a 2,000-year-old wall? The 2017 Tobermorite discovery answered why Roman marine concrete keeps strengthening underwater. It did not yet explain why above-ground Roman concrete also self-heals when cracked. That answer arrived in January 2023 in a paper published in Science Advances by Admir Masic at MIT, working with Linda Seymour, Janelle Marat, and collaborators at the Wyss Institute at Harvard and laboratories in Italy and Switzerland. For decades, archaeologists had noticed small white inclusions scattered through Roman concrete samples. millimeter-scale chunks of bright calcium carbonate they called lime clasts. The standard interpretation was that Roman workers had simply mixed concrete poorly. Masic refused to accept that. The Romans had perfected this material across centuries. They would not have tolerated sloppy mixing on the most important construction projects of the empire. His team analyzed the lime clasts using scanning electron microscopy, X-ray diffraction, and Raman imaging. The crystal structures and isotopic signatures told an unambiguous story. The Romans had been using quicklime, the unreacted form of calcium oxide, directly in the dry mix, instead of the slaked calcium hydroxide modern concrete uses. When water hit the dry mixture, the quicklime reacted exothermically. The whole batch heated up. Masic's team called it hot mixing. It trapped the lime as small, brittle, highly porous reservoirs of reactive calcium throughout the matrix. Then, when a microscopic crack later opened in the concrete and water seeped in, the water dissolved calcium from the nearest lime clast and carried it into the crack, where it precipitated out as fresh calcium carbonate, sealing the crack with newly formed crystalline rock. In a 2025 follow-up, the same MIT team examined raw material piles preserved at an active Roman construction site, frozen in time by the Vesuvius eruption at Pompeii. They confirmed it. Intact quicklime fragments were pre-mixed with volcanic ash before water was added. Exactly the hot mixing protocol the chemistry predicted. The walls heal themselves, not as poetry, as measurable, peer-reviewed chemistry, replicated in modern lab samples that scientists have cracked, run water through, and watched seal themselves shut. Part 5. How to build one. The field protocol. Lime-stabilized rammed earth is not theoretical. It is being built today across rural France, northern Spain, parts of Morocco, the Loess Plateau in China, the American Southwest, and increasingly Australia and New Zealand. The protocol below consolidates 9,000 years of practice with 3 decades of materials science research. Step 1. The soil. You do not want topsoil. The organic content rots and leaves voids. You want subsoil, the layer 6 inches to 3 feet below the surface. Target composition is 15 to 30% clay, with the balance silt, sand, and small gravel. Field test. Wet a handful, squeeze it tightly into a ball, then try to break the ball cleanly in 2. A clean fracture means correct clay content. Crumbles too easily means add more clay. Deforms like soft dough means too much clay. Add sand to balance. Step 2. The Pozzolan. If you have a wood stove or brush fire pit, sift cooled ash through a window screen to remove charcoal. The whiter the residual ash, the better. Complete combustion produces the most reactive silica. A 2019 University of Oxford study by Lucy Foussade and colleagues, published in Construction and Building Materials, identified 20 to 40% wood ash as the optimum pozzolan content for lime mortar in damp environments. Wood ash genuinely behaves as a pozzolan, despite being below the formal silica content threshold, because its fine particle size dramatically increases reaction surface area. No wood ash? The Theodosian fallback works perfectly. Crush fired clay bricks from any demolition site and screen the dust to the same fineness. Rice husk ash and sugarcane bagasse ash also qualify if combustion was complete. Step 3. Lime and mix proportions. Buy type S hydrated lime from any masonry or agricultural supplier, roughly $8 to $15 per 50-pound bag. Type S is fully slaked and significantly safer than quicklime. Wear nitrile gloves, eye protection, and a P100 respirator when handling the dry powder. Lime burns are real and accumulate slowly. You may not feel them until 20 minutes after exposure. A 2022 University of Granada mechanical study by Avila, Puertas, and Gallego, identified 12% lime by weight as the optimum for compressive strength in lime-stabilized rammed earth. By volume, roughly 1 part hydrated lime, 1 to 2 parts ash or brick dust, and 7 to 10 parts subsoil. Mix the dry ingredients thoroughly first. Add water gradually until you reach roughly 10 to 15% moisture by weight. The mixture should look like damp, coarse breadcrumbs, clumping tightly when squeezed, but not sticking to your skin. Step 4. Formwork, tamping, cure. Set up parallel boards 18 to 24 inches apart, braced firmly. For garden walls under 4 feet, exterior-grade plywood works. For taller walls, use steel reinforced framing. Pour the damp mixture in 6-inch lifts. Tamp each lift, by hand or pneumatically, until the volume compacts to roughly half its original height. The sound of the rammer changes from a soft thud to a sharp, ringing strike when the lift is fully compacted. That sonic signature is your signal to move on. Under compaction is the single most common failure mode in modern rammed earth projects. After 24 hours, strip the form and reset for the next section. Mist the wall lightly with water once a day for the first week. Pozzolanic chemistry needs continuous moisture to keep the calcium silicate hydrate gel forming. Handling strength is reached at about 30 days. Design strength at about 90. Full strength continues to develop for years. The Granada team's data showed strength still increasing measurably past 100 days, with the asymptote not yet reached. Walls built to essentially this protocol in late 19th century rural Leon in northern Spain and across the Les Plateau are still load-bearing today. No rebar, no chemical sealants, no maintenance schedule. Part 6. Honest limitations. Here is what the construction industry will not put in a sales brochure, and what I will not skip past either, because if you are going to build a structure that outlives you, you need to know what this material genuinely cannot do. Code and permitting. In most United States jurisdictions, lime-stabilized rammed earth is not a recognized prescriptive material under the International Residential Code. You will need a structural engineer's stamp on a calculation package and sometimes a variance hearing. New Mexico, Arizona, parts of Australia, and parts of New Zealand have prescriptive codes for stabilized earth. Most other places do not. Plan for paperwork. Tension loads. Earth walls carry compression beautifully. They cannot carry tension. They cannot replace steel rebar in a beam, a cantilever, a multi-story floor diaphragm, or a basement retaining wall holding back saturated soil. For those, modern reinforced concrete is genuinely the better material. The right use cases for rammed earth are single-story homes, low-rise commercial structures, garden walls, root cellars, storm shelters, agricultural outbuildings, and thermal mass interior walls inside a frame structure. Earthquake performance. Unstabilized rammed earth in seismic zones has a mixed historical record. Lime stabilization significantly improves it, and adding fiber reinforcement, natural jute, polypropylene mesh, or chopped straw brings performance much closer to modern code expectations. But if you are building in a zone with peak ground accelerations above 0.3 G, hire a seismic engineer. This is not a place to learn by experiment. Water management. Rammed earth hates standing water. The wall needs a stem wall of stone or concrete lifting the earthen section above grade by at least 8 to 12 inches, and a roof overhang projecting roughly half the wall height beyond the wall face. Skip either, and the base will fail within a decade. Roman engineers understood this perfectly, which is why so many of their above-ground concrete structures sit on stone plinths. Skilled labor and cure time. Properly tamped rammed earth is harder than it looks. If you cannot find a contractor with prior projects you can physically inspect, build a small test section first and break it open at 90 days to see what you actually got. Better to learn on a garden wall than on a load-bearing house. And if you need a structure standing in 2 weeks, this is not your material. Drywall and Portland cement go up faster, period. The trade-off is service life. The Roman version is still standing after 2,000 years. A modern lumber and drywall house has a planned obsolescence of about 40. Ballistic performance. Independent field tests on compressed earth blocks at 18-inch wall thickness have stopped multiple .50 caliber rounds without full penetration. Lime-stabilized rammed earth at 24 inches, properly compacted, will absorb most common rifle rounds at typical engagement distances. Performance depends on density, lime content, moisture, and projectile type. Treat this as a useful side benefit of mass and density, not as a marketed bullet resistance rating. Rammed earth does not replace every modern material. What it does, when applied to the right building, is outperform reinforced concrete on lifespan, thermal mass, indoor air quality, and embodied carbon by margins large enough that the engineering trade-off is worth understanding. Closing. What Mehmed's cannon couldn't tell you. The Basilica cannon was, in 1453, the most expensive piece of military hardware in the world. 2 months to cast at the Imperial Foundry in Adana. A crew of 400 men and 60 oxen to drag the 140 miles to Constantinople. Its barrel cracked apart from its own discharge before the final assault, and it sat silent on the morning the city fell. What it broke against was not exotic. The mortar that absorbed Orban's 1,200-pound stone shot was made of 3 things: dirt, lime, and powdered fired brick. The same 3 categories of material, earth, calcium, and reactive silica, that built the Pantheon's dome 1,000 years earlier, that line the harbors at Pozzolan where Marie Jackson's team is still drilling cores, and that built the lime-plastered houses at Ashikla Hoyuk in central Anatolia 9,000 years before any of the others. The chemistry was figured out before writing existed. It is the same chemistry MIT, UC Berkeley, the University of Granada, and the University of Oxford have been independently rediscovering across the last decade. None of it is new. None of it is patented. None of it is proprietary to anyone. The reason the formula faded from mainstream construction is not that it was hidden. It is that it did not fit a 20th century supply chain, and a 20th century supply chain is not a permanent feature of human civilization. Markets shift. Soils don't. If you are sitting near a wood stove, a fire pit, an agricultural field, a brickyard, or any clay-bearing soil, the active ingredients of the strongest, longest-lasting, most fire-resistant wall material humans have ever produced are within 100 feet of you right now. The cannon that broke against Constantinople was beaten by the same 3 ingredients you can dig, sift, and mix this weekend. That is not romance. That is the geological inventory of every continent humans live on. This has been Oracle Prime. Stay curious, stay resilient, build things that outlive you.